am Dr. SarahGraham. I am an ICL consultant for Integrated Environmental Solutions Limited. In this presentation, I will look at the application of digital twins and the future of sustainable analysis of the built environment against a backdrop of climate emergency and Industry 4.0. The uptake of digital twin technology is accelerating within the construction sector and looks set to transform how we design, build, operate and use the built environment. Static BIM models are evolving into digital twins to create value, particularly through design and construction. However, the opportunities presented in terms of operational performance and, more importantly, decarbonisation of the built environment using digital twin technology remains largely unexplored. Using real-world examples, I will illustrate how physics-based simulation and artificial intelligence, Internet of Things and machine learning can come together to create future scenarios and determine the most effective, energy and resource efficient decarbonisation strategies for any building or group of buildings. I will set the context by reviewing some of the challenges of achieving net zero greenhouse gas emissions, of which carbon is the largest contributing factor. I'll look at how supply of energy is changing in the UK, some of the Industry 4.0 technologies coming through and how they are being applied to the built environment. I will then focus in on how the technologies and approaches can be applied to the problem of decarbonisation. I will review two recent case studies to highlight the wider benefits of digitising design and operation of our built environment. According to the IPCC, scenarios giving a 66% chance of holding temperature rise below 1.5 degrees are already out of reach. The United Nations Environment Programme Emissions Gap Report, published in 2019, states there is no sign of greenhouse gas emissions peaking in the next few years. This report also states that by 2030, emissions would need to be 25% and 55% lower than 2018 to put the world on the least cost pathway to limiting global warming to below 2 and 1.5 degrees respectively. By 2050, the world's urban population will have reached 6.3 billion, and 2/3 of the people on the planet will be living in urban centres. So despite effort and commitment, carbon emissions are not reducing globally. In light of the COVID pandemic, there is a further impact potential on carbon emissions of buildings moving to full fresh air. One solution comes in the form of scaling up of climate action from individual sectors to a more holistic, integrated view of decarbonisation of city operations, infrastructure and services. Smart energy communities, zero carbon districts and positive energy blocks are some of the most recent descriptions of district and community level schemes. In a white paper produced last year, Scottish Power Energy Networks highlighted that the energy sector is undergoing multifaceted changes in terms of decentralisation and decarbonisation of energy networks. They predict growth of between 10 and 20 times the energy generated by community schemes against a baseline of 280 megawatts in 2018 by 2030. The path to a decentralised, decarbonised and digitalised energy landscape begins with a transition architecture to a low-carbon energy system. The next step is to optimise the energy mix, fully integrating renewables. Then apply energy storage to increase flexibility whilst maintaining reliability and performance, using data analytics to anticipate demand and empower users, and finally, aggregation of distributed domestic and commercial energy sources into virtual power plants. Data and analytics are key to the success of these larger schemes with their multidimensional complexities. To realise the potential across different sectors, planners, designers, managers and users require robust tools. Digital twin platforms can provide the complex modelling, analytics and simulation capabilities needed to support diverse stakeholder groups. The extension of building systems from standalone applications focused on the operation of a single building to hubs within a wider network of energy and environmental monitoring will be one of the most dramatic changes in the technical infrastructure of the city. Navigant research estimates that less than 1% of the commercial building stock globally is actively participating in the energy system. but over the next decade this will rise to more than 10%. Cities around the world have signed up to the Paris Accord, and many more have set out plans to achieve zero carbon by 2050. To make those commitments a reality, a reduction in urban emissions requires increased focus on transforming energy use in buildings and transport, as well as a shift from fossil fuels to renewables, and a holistic approach to decarbonisation. Cities will become clusters of smart energy communities that can exploit the benefits of new energy systems demonstrated by the virtual power plant or the positive energy block example, whereby demand and supply are optimised at a local scale. In the same time frame, the advance of the fourth industrial revolution is making cyber-physical systems in the built environment practical, useful and affordable. Gartner predicts that by 2021, half of large industrial companies will implement digital twins, resulting in at least a 10% improvement in effectiveness. Industry 4.0 describes the trend toward automation, data exchange, and processes including cyber-physical systems, the Internet of Things, cloud computing, cognitive computing, and artificial intelligence. Digital twins are a computerised model of a physical system or device representing all functional features and links with the working elements, and thereby encapsulate Industry 4.0 principles. The results of the KPMG Global Construction Survey 2019 indicate that the construction industry is moving in the right direction in terms of technology adoption. The report concludes that 52% of innovation leaders agreed that machine learning and artificial intelligence will be commonplace within the construction sector within 5 years. On the top right here, we can see that of those surveyed, the majority agree that digitisation of construction will improve productivity and delivery, assist in tackling sustainability, and help to improve health and safety. The stack chart in the middle of the slide indicates that the majority of firms are at the early stages of their digital transformation. Within the built environment sector, designers, constructors, owners and operators are beginning to explore potential productivity gains of deploying digital twins. The Centre for Digital Built Britain sets out the benefits of an ecosystem of digital twins, or a national digital twin, to the tune of £7 billion per year across UK infrastructure sectors, largely as a result of reduced risk around cost and schedule overruns and the ability to predict issues on site before construction begins. However, one of the largest opportunities for the built environment is to optimise urban sustainability by creating a virtual replica of any city or community as required in order to achieve carbon commitments. The Centre for Digital Built Britain defines a digital twin as a realistic digital representation of something physical. What distinguishes a digital twin from any other digital model is its connection to the physical twin. Some progress has been made through implementation of BIM on projects in terms of centralised, accessible and structured information. This forms a solid foundation for the implementation of digital twin technology and has helped practitioners and their clients to understand the benefits of digitalised and structured data. The addition of real-time sensors and machine learning to process large amounts of data, combined with the power of physics-based simulation, delivers the vision of a digital twin for construction. And this is an important distinction between a typical BIM model and a digital twin. A digital twin not only looks like the building, it behaves like the real building, responding to operational conditions and building occupancy to produce an invaluable operational asset. There is already a considerable amount of data in buildings that can be useful in optimising operational performance and reducing energy. The amount of data will grow with the advancement of IoT, but we need robust mechanisms to capture and process the data. The context of this presentation shifts the focus of decarbonisation from the design of new buildings firmly to the operational optimisation of medium to large scale existing developments to meet 2050 targets. I have two case studies that I want to go into in a bit more detail. The first is one of the lighthouse cities on the Positive City Exchange project, part of the European Commission's programme on Positive Energy Districts and Neighbourhoods, PED programme. The PED programme aims to support planning, deployment and replication of 100 PEDs across Europe by 2025 for urban transition and sustainable urbanisation, and as such, it is one of the most ambitious visions for community action on climate change. The project looks at energy, transport, building upgrade and social development. Limerick has been selected as one of 2 lighthouse projects, and the City Council is leading the implementation of 11 demonstration projects in the city and are exploring the following initiatives towards creating a PED. Reducing energy demand through improvements to building envelope, replacing fossil fuels with heat pumps and solar PV, integrating technologies at a building and district level, e.g. district heating and community storage batteries, installing building energy management systems to ensure optimal operation at the community and building level and to facilitate interaction with the smart grid and potential future connection to energy trading platforms. A key aspect of the Limerick project is the integrated view across energy, buildings and transport, as well as understanding the impact of change on various groups within the community. Digital twin technologies are deployed to collect data from multiple sources, to analyse the impact of proposed interventions and understand interdependencies among different elements of the city. The digital twin has been created to assist with visualising current energy demand across the buildings and their networks to identify priority areas for investment. The digital twin is also used to aggregate metered data from buildings and systems and deploy machine learning to calibrate the virtual model to its physical counterpart. Using the virtual model then to test different scenarios, for example, adaptation to future climate predictions, modifying demand profiles, alternative energy sources, energy storage, and an increase in number of electric vehicles connecting to the network. The digital twin provides socio-economic context in the form of population structures, social indicators for health and well-being, education, employment and housing. The digital twin is used to facilitate stakeholder engagement and ongoing operational optimisation, evolving alongside the community scheme. The outcomes of this project will inform other cities as they look to meet their own commitments with respect to energy and carbon reduction, as well as understanding how digital twin technology can be deployed as an enabler. As well as demonstrating technical innovation, community energy schemes driven by digital twin technology provide opportunities for cities to take control of their own energy systems. Behaviour of building users and their engagement with the systems are as much part of the success of the scheme as the technical components that enable new approaches to generation and distribution of energy. The Trent Basin Development Project SEEN is part of a £100 million regeneration project in Nottingham. The aim is to accelerate the adoption of community energy systems to reduce cost and carbon via local energy generation. Development comprises over 145 low-energy homes, a large solar PV array, and, at the time, Europe's largest community battery installation. The live interactive digital twin is driven by a 3D model of the entire site overlaid with real building data, local weather data, data from the PV array and the on-site electrical storage battery, affecting the cyber-physical connection. The digital twin also monitors occupant comfort and compares the real-time data against a modelled or anticipated set of results to draw insights into occupant-driven outcomes. The residents become active players in their local energy systems, and designers of such schemes gain an understanding of occupant behaviour as a major factor in overall energy consumption. The digital twin is accessible via an online platform, informing residents of the performance of the scheme, so residents can log in and they can see what's being generated on site, what's being used and what's being stored in terms of energy at any time. The data is presented in a digestible format so they can see what's happening, and there are automated comparisons each time step between the calibrated virtual model and the physical model. So if, for example, the PV is not performing as expected, this is flagged for the team via the interactive display and they can intervene as necessary. So just to draw all of that together and in conclusion, decarbonisation needs to happen at scale if we are to have a chance of achieving the targets set. We already have a lot of data at our disposal, and that is set to grow. Digital twins encapsulating Industry 4.0 are accelerating creation, capture, management, automation and visualisation of large amounts of data and insights. The construction industry is at the early stage of capitalising on structured information related to buildings with a view to deploying digital twins to better understand buildings. Some of the challenges include buy-in at all levels to move to a more digitised way of working and delivering projects. Construction procurement by its nature is fragmented. The aim is to avoid data and technology for the sake of it. The question should be, from a business or organisational perspective, what problem are we trying to solve? What tools and what data sets do we need in order to tackle that problem? Technology is evolving in all walks of life and in most cases leapfrogging policy, so the aim is to remain agile, build a technology stack that can support dynamic capabilities and adapt quickly to new challenges and opportunities. My contact details are shown on the screen, sarah.graham@iesv.com, and the number is 0141 945 8500. Please do contact me if you have any questions or wish to follow up in any way. Many thanks.